This is video 35 in the lectures on the design of reinforced concrete beams. This lecture deals with the deflection of concrete beams. A first video will be handling the calculation method, and in a second video we will give an example. The curvature of a line as y in function of x is defined as 1 over the radius, or it can be written as the second derivative of y divided by the first plus divided by 1 plus the first derivative squared, and this to the power 1.5. This is the definition of a curvature. When the first derivative of x is smaller than 1, then we can make an approximation that the curvature, or 1 over the radius, equals the second derivative of y to x. We look now at the beam, a section before loading, section after loading. If this is the angle alpha and then the depth of the neutral axis is phi, then we know that when the first derivative of a is small, that tangent alpha is equal to alpha when alpha is in radians, expressed in radians. Alpha is then epsilon divided by v, and alpha is the radius 1 over r, or is the curvature 1 over the radius. We have seen that the curvature equals the second derivative, so the second derivative equals alpha equals epsilon over v, but epsilon equals strain divided by the modulus of elasticity, strain divided by modulus of elasticity. But the stress equals the bending moment divided by W, and W is the moment of inertia divided by V. So we see that the second derivative equals m over EY. So now if you want to calculate the deflection or the sag of a beam, we just have to solve this simple equation by direct integration. So that's quite easy. It's just the bending moment in function of x, and you make the integration. But now we have a problem, because if you want to do that, AE is not constant. It is certainly not constant over the whole length of the beam, because AE varies according to the section, if it's cracked or non-cracked. So this poses a problem for the direct integration. When the bending moment is always smaller than the cracking bending moment, then of course AE is constant when the section is constant and the reinforcement is constant. All that must be constant before EI is a constant, before the stiffness is constant. So stating this, that if the section is not cracked, AE is constant, is not entirely true, because the section must be constant and the reinforcement must be constant. When the section is cracked, then AE varies together with M. To illustrate this, if you have, this is the bending moment, then we have here the level of the cracking moment, cracking bending moment. This is the maximum bending moment in the section, and we plot now here the deflection. Then you will see that it is almost linear from 0 until the first cracks appear, and then it starts deviating from linear until it reaches its maximum curvature, where the bending moment is maximum. This is because of the section is more and more cracked. If you make a plot bending moment with curvature, then you can see clearly that there are two different slopes, one with the uncracked section and one with the cracked section. So calculating the maximum sag of this beam is in fact a combination of non-cracked, partially cracked, and totally cracked. The mean curvature in a cracked section is then m over AE, but then in the mean value, and m over AE we have seen it's delta epsilon, the strain, the difference in strain of steel and concrete, but the mean value divided by D. The cracking moment, just to recall, is the bending moment at which the tensile stress in the concrete is equal to the mean tensile stress. So the cracking moment is FCTM times W. W is E over V accent or V. Or you can also say it's H times minus X, because now we are here at the lower part. And if you take the tension of the section at the bottom of the section, then this is V accent. Okay, this is for the uncracked section. So the cracking bending moment is calculated with the moment of inertia of the uncracked section, non-cracked section. FCTM is for concrete quality smaller than C50 is equal to 0.3 FCK to the power 2/3. Moment of inertia of a non-cracked section that we have seen in the previous lessons is equal to that. The depth of the neutral axis, because there is an x1 in, the depth of the neutral axis of fictive cross-section, non-cracked section is equal to that. So this is no more or no less than the point of gravity of the fictive cross-section, and this is the moment of inertia of the fictive cross-section. The fictive cross-section is the compressed concrete section plus alpha times the steel. The moment of the cracked section is given by this equation, and then the depth of the neutral axis of the fictive cracked section is then equal to this. So we have now 4 expressions. We can now calculate the stiffness of a cracked section. The EI of the cracked section is then the EC and E2. It's the moment of inertia of the cracked section. Of the non-cracked section, it's similar, but EC E1. We can calculate the curvature of a cracked section is then M divided by EC E2, and the curvature of a non-cracked section is M divided by EC E1. EC equals the mean value ECM divided by 1 plus phi, with phi the creep factor. Now we can take a graph where this is the bending moment on the y-axis, and on the x-axis is the curvature 1 over r. You can calculate for the uncracked section. We see that this line represents this line, and for the cracked section, completely cracked section, it's this line. Reality is somewhere between the two. But at increasing bending moment, it's in the straight line, and you stay here on the R1 line. When you reach the crack, when the section is cracked, you have a disturbance, a redistribution, and then you start again, but this time you move towards the R2 line. This is the mean curvature. This is the uncracked curvature, cracked curvature, mean curvature. And we state that for a bending moment when the section is cracked, then the mean curvature is a linear combination of the uncracked and the cracked section. And the coefficient zeta depends on the steel stress at cracking moment divided by the steel stress of the cracked section multiplied by a coefficient B. A situation where the concrete is cracked can then always be described as a combination alpha with 1 min zeta alpha 1, and alpha 1 is non-cracked and zeta cracked. So you always have a combination of a non-cracked with a cracked section. And the coefficient zeta, as we have seen, is this value. The value of beta is 1 for short-term loading and 0.5 for long-term loading. And zeta is when you are sure that the section is not correct at all, then of course zeta must be taken as 0. You can now estimate the sag of a beam in a cracked section situation, and next lecture we will give you an example how to do it.